So, very good morning, dear all. After a long time, we are present here to discuss about our issue related to digital communication. Already, I have discussed lots of things related to digital communication, and I have discussed related to the issues of various modulations, amplitude shifting, phase shifting, and frequency shifting. I have made few PowerPoint presentation for you only, and just I want to share those PPT for you. Just look. Uh, this is the first issue where you will get this modulator. Before that, rest of the parts related to the baseband modulation. There are two things already I've discussed: baseband modulation and band pass modulation. So in case of our carrier modulation, we have discussed this part: modulators, how much noise are effective for any modulation. And regarding this issue, we have discussed about probability of error and how much error that can be found. Based on that, we have analyzed some performance of the system. I will tell you later in this discussion. Already I have discussed the detectors, various detectors in our communication system related to carrier modulation. The binary digital modulation and A-Mary digital modulation and their comparison study. This is the first issue. Next to that, digital modulation already I have discussed. ASK is related to AM, FSK is a special case of FM, PSK is special case of PM. Next to that, uh, already I have discussed few mathematical expressions for BPSK. You know what? This is the mathematical description. There have one 0 degree phase lag, whereas in case of zero symbol, there have pi phase lag. That means if I can analyze it using some uh, energy constellation diagram, we have found there have 2 points at the axis of our base point, and that is called basis function. In case of basis function phi 1t, we have two energy points. Those are absolutely 180-degree phase shift relationship in between them. Next to that, we have found there have some equal probability distribution, and regarding that issue, we have computed some probability of error. This is the way to compute our probability of error. So this is the region where 1 may be replaced by 0 and 0 may be replaced by 1. So we have found our error in this region only, and we have found it. The error may be computed using complementary Q function. You may obtain it using your complementary error function, ERFC function. Next to that, this is the function where we have found the relationship between energy to noise ratio. So obviously, if you can compare with respect to any modulations, you must put at the x-axis what kind of parameter that should be the average power to noise ratio. That means effective energy, bit energy to noise ratio, which is known as your mean power, mean transmit power, or it is known as the uh, effective uh, SNR, mean SNR. Okay, and what kind of energy it is? It is beat energy. Already I have discussed everything, and this is the BPSK transmitter. You know everything. You know BPSK receiver. You know the binary FSK. What is binary FSK? The frequencies are different. Here it is F1, it is F2, and when I can compute the energy per bit, that may be computed using this way, right? So same thing like our BPSK, and already I have discussed delta F is selected so that S1T and S2T, they are orthogonal to each other. So when we can compute it over the interval for a bit, then 0 to TB, if you can integrate it, you will get simply 0. And when I want to replace it in our uh, BFSK signal space diagram, that may be shown as this is the our basis function, first message point S1, for which for the representation of our 1, S1T for 1 and S2T for 0. So when you can replace it, then root TB, this S1 for 1 and S2 for 0. If you can compare them, you will get some orthogonal relationship in between them, right? And ultimately, you will get some decision boundary point in between them, and we can compute the probability of error. This is the final probability of error, which is something different as compared to our BPSK. What is written over here? IID, independent, independent, and the distribution should be uh, same. Okay, this is called IID. That means the distribution everywhere, that is everywhere same. Okay, same distribution around the certain particular point, and it is known as IID. When I'm talking about BFSK, I can compute the probability of error, and I have written that BFSK needs 3 dB more transmission power than BPSK. So as compared to BPSK, BFSK needs 3 dB power, means when it will get more power, it will perform better, or it will perform like the BPSK, right? Sorry. When I'm talking about the BFSK transmitter, this is the BFSK transmitter. Already I've discussed in the previous classes. This is the receiver. Receiver means what I need. I told you there are two things. One is coherent receiver, non-coherent receiver. I will discuss everything, and uh, before this class already I have uh, discussed so many things regarding coherent, non-coherent receivers, and I told you what is the meaning of decision device, and when it can switch to 1, that means some threshold value is less than our output of this L. Then I'm getting the output as 1. When the threshold value is greater than this L, I'm getting 0. When I'm talking about ASK, what about the ASK? ASK is something like that. That means on-off keying. I have discussed everything. There are some region in between these 2 points. One region is related to some presence and some is absent, and you will get some difference in between them. Probability of error that may be discussed using this complementary Q function. After that, if you can compare it, everything is written over here, right? And what you know, I told you, this energy may be computed using what? The distance between the two consecutive uh, state points. That is T12. If we can compute it, then we will get this EB. Okay, EB that may be computed using this distance. So when we can compare in terms of the graphical plot, we are getting what? The PSK performs better in terms of bit error performance. It needs less energy to obtain this amount of probability achievement. So this probability that can be achieved at a very less energy to noise ratio. On the other hand, when ASK and FSK that can achieve this amount of probability of error, it needs more energy to noise ratio. So everything is discussed in terms of some coherent, non-coherent basis. And I told you in the previous classes that DPSK is more essential as compared to DPSK when I need non-coherent detection. In this regards, I have discussed everything in terms of our BFSK also. So this is the vector points and how to detect your PFSK, FSK signals that is written over here. And in terms of that, every points, basis points that may be used over here. Okay, and what is this? It is your blood, and it is also known as your integrator that may be used as desampler. Actually, detector means what I need, just opposite thing. Basic issue is same, but the action is just opposite, right? Sorry. Various things related to mathematics, non-coherent FSK. Already I have discussed it. So next, when I want to compare the performance uh, in terms of BPSK, ASK, non-coherent FSK, DPSK, FSK, what we are getting? We are getting best performance using BPSK. After that DPSK, next to that ASK or FSK, and last one is NCFSK. What does it mean? Non-coherent FSK. So when energy to noise ratio is more, then we are getting the same kind of performance using NCFSK. DPSK, I have discussed it. What I need XNOR operation between the extra bit and the present message, and you are getting some phase. Using that, you can implement it using your transmitter. And this is the detector, DPSK detector, you know everything. If you can compare them, you will get exact probability distribution in terms of PSK, ASK, FSK, non-coherent FSK, DPSK. And everything is written over here in terms of their distribution. What is written over here? Please look at this. Everything is written in terms of Q function. On the other hand, DPSK means what? DPSK means the comparison between the same signal and delayed signal, and then you are getting in terms of exponential function directly, not like Q function, complementary Q function. Okay, so it can be defined using your exponential function, direct exponential function. We do not need any definition like Q function. Next to that, when I'm talking about the AMRE digital modulation, then how to use that AMRE digital modulation, already I have discussed everything about AMRE PSK, which is known as MPSK. Now today we are going to discuss about AMSK, MFSK, something I have discussed about MQM. 16 QAM, I have discussed it. Now today I'm going to tell you what is MPSK. I have discussed, and that is written over here, nothing else. If it is BPSK, then the figure something like this. When it is QPSK, there are 4 points. When it is 8PSK, 8 points. When it is 16PSK, then 16 points. Okay, and next to that, you can compute your symbol error probability. I told you, using some mathematical derivation you will get it from your Higgins, that the distance between two consecutive points that may be computed using Euclidean distance, and that may be found as the complementary Q function like this. And if you can compare them, you will get what? Obviously you will get something like this figure, where just look, the output is absolutely better for the BPSK. Equal to 2 means what? BPSK. 4 is QPSK, 8 means 8PSK, 16 means 60. So if the the number of value which can be found using M is greater, then you will get the performance is quite poor as compared to BPSK. Okay, for M equal to 2, the performance is exactly better. Next 4, then 8, 16, 32, 64. It means I need more energy to achieve same error probability. Same error probability that can be achieved, but I need more energy to noise ratio. That means my signal energy requirement is more. What is MQAM? I told you, this is the figure MQAM. Okay, 16 QAM, 16 points are there. And what is the benefit? I told you, more number of bit transmission that is possible. So your data rate is quite higher. Another benefit, but the problem is something like that. This is the lattice, square lattice figure. Uh, one in phase component, what Richard was phase component, it is 64 QAM when the block is larger. When the block is quite smaller, you are getting 32 point, next to that 16 point, after that 8 points, and last one is your no more 8 point. 8 point means obviously 8 PSK that may be implemented, but it is not possible for MQAM. It is always the relationship of your 4, 16, 32, 64, next to that your 128, 256, then 512, something like that. So this is the constellation diagram, and you will get your performance measure using the upper bound computation. What you know, when the error probability or anything with the closed form computation is quite critical, when the closed form solution is quite critical, we want to find the lower bound and upper bound. Lower bound means this is the minimum value requirement for some power consumption. If I am if I want to compute some power requirement, that means lower bound means this is the minimum energy requirement, minimum power requirement. Upper bound means maximum power. If you go beyond that, then the system is not is not perform like the exact nature, because the power requirement more means what, your system efficiency, energy efficiency is very poor. So what I need to maintain some limit. On the other hand, in case of performance measure, you need to maintain the least value. If you go be less than that, then the system performance is quite poor. So why should I go less than that? I need to maintain something like this, or the probability of error must be present up to this limit. So the probability of error not beyond certain limit, that means probability of error should be bounded within lower bound, not up to the upper bound. Upper bound is relaxation. Why should I go beyond that? So probability of error must be bounded within a certain lower limit, and that may be computed using this way. Okay. MFSK absolutely used for multi-tone signaling, and that may be computed using some correlation computation between two symbols, and we are getting this thing because MREFSK. What is MREFSK? MREFSK something like our MPSK, 8 PSK, 16 PSK, something like that. Already we have computed some power spectral density. We have computed the power spectral density for PSK, ASK, FSK. We have found the impulse that may be obtained at the center frequency, and around that one sync may be obtained for your PSK. In case of your ASK, that impulse or delta function may be absent. In case of your FSK, two sync function may be coincide at a particular point, and around that one center frequency is there, another center frequency is at the right side. Um, this is the error performance measure of FSK. If you can look at this, what we have found in case of MPSK, if the value, if the m order of m is less, then we are getting the performance is better. On the other hand, in case of our MFSK, when the order is higher, then we are getting better performance. Just opposite of that. Okay. So this is the comparison. You can note it, the very important measure and probability error calculations. Comparison, I told you everything. There are two most important parameter: energy efficiency and bandwidth efficiency. And channel bandwidth, transmit power are two primary communication resources for any MRE modulation techniques, and their comparison purpose, this is the most important thing, transmit power, because if I know the transmit power, then we can compute EB by NO. and everything is written over here. uh, Obviously 3 dB or 2 dB calculation, same thing like the fundamental trade-off is shown in terms of minus 1.59 dV. EV by NO is written the ratio, and this value is called as the Shannon limit, and this is most reliable communication limit for information theory purpose. We know that, and MQM is superior to MPSK. Um, BPSK and QPSK require same EV by NO to achieve same probability of error. QPSK has a better bandwidth efficiency. MPSK, MQM increase bandwidth efficiency. MPMFSK states the energy efficiency at reduced bandwidth efficiency. This is also important measure. So if you can look at this last part, this is the absolutely main comparison measure. Okay, thank you.